In the part 1 of this tutorial, we simulated the velocity profile between two plates where the bottom plate was at rest and the top plate was moving with a velocity Vx naught, which was 1 centimeter per second. In this part, and then we plotted the velocity profile at the midpoint. In this part, we will consider that the top plate is now moving, is actually oscillating with a velocity a sine omega t, where a is the amplitude, which is given as 1 centimeter per second, and angular velocity is actually this is a 2 pi per second. And we will be considering two cases. In one case, viscosity is 0.1, and in another case, viscosity is 0.5 pi. So let's go back to our COMSOL model. So this was our COMSOL model. We have to enter the new parameters. Go to parameter and type A, which is amplitude, and this is 1 centimeter per second. Okay, and the angular frequency omega, we have to enter that as well. Angular frequency is 2 pi per second. Now go to the component, click on the laminar flow, and we have to change the condition of the wall 2, because now this wall is again a sliding wall, but now it is oscillating with a velocity of a static sine omega t. Okay, this wall is oscillating with this velocity. Now go to the study, and here we have to enter the ranges, the output time ranges where we want to see our results. So the first range is 0, 2, 18. That means that it will give us result from 0 second to 18 second with the interval of 2 seconds. Another range is from 19 to 20 with an interval of 0.25 second. Okay, now compute. You can compute, run the simulation, and here is the result. Okay. So at 0 time, of course, this is for this is the velocity profile at 0 time. So let us see the velocity profile at okay, this is it after 2 seconds, 4 seconds, 6 seconds, and so on. Okay, and this is the velocity profile for another range, which was from 19 to 20 with the interval of 0.25 seconds. Okay, we can also see the line graph. So just go to 1D plot group and then select the time interval, which is 19 to 20. So please keep in mind that this 1 second was actually, this was the frequency of oscillation, sorry, the period of oscillation. So we will just rename this and just delete this and type new names. So this blue line is actually for 19 second, another one for 19.25, the green one, and this maroon one is for 19.5, and then 19.75, and this last line, the purple, it is for the 20 second. So this is actually the velocity profile that we can observe between the plates when the top plate is moving, is oscillating at a velocity of a sine omega t. So here you can see this the velocity profile at 19.25 seconds. So at this time the plate is moving forward, so all the liquid which is attached to the plate is also moving with the same velocity. You can see this green line. So the fluid which is just adjacent to the plate is moving at the same velocity, and as we move away from the top plate, as we move downward from the top plate to the bottom plate, the velocity decreases, and it is 0 at the bottom plate. So you can see this velocity profile here, and let us also observe this on the surface. Here you can see the velocity profile at okay, let me just select the 9.25. So this is the velocity profile. You can see at this timer the plate is actually moving to the right. Now, okay, this second line, this red line, this is actually for 19.5 second. At this moment, the plate is at rest. It actually reached the right side. So if the plate is at rest, that's why the liquid adjacent to the plate is also at rest. However, the liquid below the plate is still moving with this velocity. Still moving with the this velocity. We can see this on the surface. So if you go to the velocity and then click on this time and select 19.5. So here you can see that all the liquid which is just adjacent to the top plate, that liquid is stationary, that liquid is not moving, it has zero velocity because of the no slip condition. However, the liquid below the plate is still in a motion. Okay, so you can see that at this moment this is the velocity profile. Now, okay, and at this line is for the time of 19.75 second. At this moment, the top plate is actually moving to the left side. So the liquid adjacent to the top plate is also moving to the left side because of the no slip condition, and you can see a negative velocity here. So that's why this velocity is a negative. So as we move downward, as we move from the top plate to the bottom plate, the velocity profile look like this. And you can see that the velocity is of course the velocity is zero near the bottom plate. This negative velocity is just because of the because the plate is moving to the left side. And when the it reaches to the left side, it's again at rest, and you can see that the velocity is zero. The velocity of the fluid which is just adjacent to the plate is zero, and the velocity is changing actually. Here you can see that this velocity, this is the velocity. Uh, sorry, this is this, and this velocity profile is for the 20 second actually, where the velocity is zero, the plate velocity is zero, the plate is stationary, so the liquid adjacent to the plate is also stationary. However, the liquid below the plate is still moving to the left side. So this is the velocity profile at 19 point this velocity profile at 20 second. So the cycle actually completes in 1 second. This is actually the period of the oscillation. uh, and this was for a fluid which has a viscosity of 0.5. Let us change this viscosity to 0.1. 0.1 gram per second and a gram per centimeter per second, and now compute. Okay, let us see the velocity profile, line graph, and now this is the velocity profile. You can see that large velocity gradient exists in this velocity profile as compared to the previous one. Here is the comparison. So the right side is for 0.1 pies, and the left side is for 0.5 pies. And you can see that due to the viscous forces, uh, due to the higher viscous forces, uh, the velocity profile look like this, right? It's look like this. Small gradient exists. Small velocity gradient exists in this case. However, for 0.15, large velocity gradient exists, and the reason is the viscous forces.